Let us start the last session of the day with Gautam Sengupta, who will talk about reflected entropy in a BCFT on a black hole background.
Okay, I'd like to thank the organizers for organizing this very interesting workshop on such an interesting topic and for inviting me here and providing me with this opportunity to present one of the work of my group. The title of the talk is Reflected Entropy in a BCFT on a Black Hole Background. Title is a little bit of a misnomer, as I will explain later on. And this work has been done in collaboration with my students, Debashish Basu, Himanshu Chaurasia, and Vinayak Raj. It's already published, and it's a slightly older work. There are newer works, but I thought that this would be best fit for the time. Debashish and Vinayak they have already finished their PhD, and they're moving to China, where Himanshu is in his final year, and will be expected to submit his thesis next year. Okay, so this is the outline of the talk. I'll have a brief introduction. Then I will try to review some of the ideas of reflected entropy, and then go on to entanglement islands and the black hole information loss problem. So for these topics 2 and 3, I'm not going to spend much time. I'll deal a little bit with reflected entropy in details, but this has been extensively already reviewed by both Raju and Tadashi. And then there's one slide for the ADS BCFT, which again has been reviewed by Tadashi. And then I will review a model by Geng, Randall, and Swanson, a kind of a brain world model. And then we'll present our calculations for the reflected entropy for BCFT on a black hole background, and then look at the corresponding page-like curves for the reflected entropy, and then I will summarize. Okay, so recent advances have provided exciting insights into partial resolution of the black hole information loss paradox in models of quantum field theories coupled to semi-classical gravity, and this involves the emergence of entanglement islands. Typically, the fine-grained generalized entanglement entropy, including the island contributions, for subsystems in radiation baths reproduce the page curve in these models. However, several questions and issues remain which require further study and progress of this critical issue. Subsequently, in a slightly different direction, the entanglement structure for mixed states in radiation baths in the context of the island formulation for different models has been elucidated in a series of studies by various groups, including us. So these utilized mixed state entanglement and correlation measures and led to the emergence of a rich entanglement phase structure, which is more nuanced than the standard entanglement entropy phase structures. And what I will do is, as an example of the above, we will describe an investigation of the mixed state correlation measure of the reflected entropy for a boundary conformal field theory in an ADS2 black hole background. This is a fixed background, it's just a curved background, it's not really a true black hole backgrounds per se, it's in 2 dimensions, of course, in a bulk brain wall model, and demonstrate some interesting phase structures and page-like curves for, this is a typo, exhibiting transitions between the different phases, okay? So I promise that this is going to be a very simple, technical computation. There are no very interesting insights, except that we can demonstrate some interesting phase structures for the reflected entropy in these kind of models. Okay. So we start with a review of reflected entropy. Parts of it has already been done by, I don't know if Tom Faulkner had reviewed this in his review lectures, but I will just be brief about this. So you consider a bipartite quantum system, A union B, in a mixed state rho AB with a canonical purification, this square root rho AB, which Pratik also described in his talk in the morning on entanglement negativity, which is defined on the doubled Hilbert space, HA cross HB, HA star cross HB star. So this is a pure state. So it's a canonical purification, and typically it has a structure like this, and this is the diagram. So it's a purification to this root rho AB. And the reflected entropy is defined as the von Neumann entropy of the reduced density matrix, rho A star, where you trace over the degrees of freedom of HB and HB star. And so this is what it is. If A union B is a pure state, it's easy to see that the reflected entropy will be either twice of the entanglement entropy of A or twice the entanglement entropy of B. And it has been shown that there are upper and lower bounds in this paper by Datta and Faulkner, that it is bounded, the lower bound is the mutual information, and the upper bound is twice the minimum of the entanglement entropy of A or the entanglement entropy of B. So the replica technique in this case is slightly more involved in the standard Cardi replica. Okay, so you construct a state psi m, so you replicate on an m replicated manifold, and m has to be even. This is like the state psi m can be understood as a purification of the state rho m AB on the m-sheeted replica manifold. And the Renai reflected entropy is then defined as the Renai entropy for the reduced density matrix rho m A star, which is given by tracing over HB and HB star of this. And finally, so you can write the Renai reflected entropy in the following form. So this requires yet another replication in the Renai index n. And this is now can be in a standard way expressed in terms of properly weighted partition functions, Znm on the replica manifold, and this is the form, where Znm is given by this expression. So finally, the reflected entropy is obtained in the replica limit, n and m going to 1, okay. There is some subtlety about the order of these two replica limits, okay. So typically, you take m first and then n, but this order could reverse depending on the subsystem sizes or the time dependence in the problem. So, but in most examples that we have dealt with, this is the order that we have followed. So just to give you a more pictorial representation of how the replica manifold is constructed. So here you have an example for rho square AB is a standard Cardi. And then this is the purification where you have A star and B star instead of A and B. And now with these units, essentially we build up the replica manifold. So this is the bra and the ket, okay? And the B is traced over, B and B star are traced over through this, okay? And just to explain this in a better way, instead of going into all these complicated things, if you look at this, so there's this matrix of the replica manifold. So there is, in this direction is N, and this direction is M. So you see the B in each of these columns is sewed together, whereas A has a more complicated sewing procedure. So this is actually A star, it's not marked there. So A star goes to A star and then back, okay? And this is repeated throughout the matrix, throughout this array. Okay. The respective partition functions now can be obtained in a standard way as the correlation functions of twist operators with sigma GA and sigma GB inserted at the endpoints of the subsystems A and B, which are disjoint subsystems, and the Renai reflected entropy can be expressed in terms of these twist correlators, which is fairly standard. But here the twist operators are slightly different in the sense that they are not strictly local, because as you can see that the A sewing is very different from the B sewing, okay? The A sewing goes, this pattern is repeated across the array. And these are the conformal dimensions of the primary twist operators. We will just have a brief review of the entanglement wedge cross-section. You can see this entanglement wedge is a codimension 1 bulk region bounded by the subsystems A and its RT surface gamma A. And the entanglement wedge cross-section is a codimension 2 surface, sigma AB, with minimal area dividing the entanglement wedge for A union B. And this is the relation that we have. Now for a disconnected entanglement wedge, the entanglement wedge cross-section is 0. So here is, this is fairly standard and very well known. Now, Datta and Faulkner proposed a holographic duality, and you can see that when you purify, then this A star A and B star, so the reflected entropy between A and B will be the entanglement wedge cross-section, which is actually doubled for A and A star, okay? So this will be twice the entanglement wedge between A and B. So this is the holographic duality. And then there is this issue of a Markov gap. So in Datta-Faulkner, the reflected entropy is shown to be bounded by the mutual information from below. And this bound was refined in by Hayden, Onkar, and Source, where the difference between the holographic reflected entropy and the holographic mutual information was shown to be bounded by the Markov gap. And a geometrical description for the Markov gap was provided in this paper. in terms of the number of non-trivial boundaries of the entanglement wedge cross-section. So you have two examples over here, in which case there are two boundary points, and for this configuration where A and B are adjacent, there is only one boundary. Very good. So this black hole information loss paradox, and this Penrose diagram is very well known, so I'm not going to go into the details of this. The Hawking process creates entangled pairs which trap behind the horizon, and the other escapes to infinity, where it is absorbed as an approximate black body radiation, and the black hole shrinks. At the end, there is a smooth space-time containing thermal Hawking radiation, but no black hole. And in ADS space-time, in the East Coast model, the large black holes in anti-de Sitter space have positive specific heat and do not evaporate. And in order to mimic the behavior of evaporating black holes, one couples the system to an external flat bath. And this is the diagram, and this is an eternal black hole. So essentially, there are two sides to this. And the fine-grained entropy of the bath subsystem containing the Hawking radiation can get contributions from region inside the black holes, which are called these islands, entanglement islands. And the entropy of radiation from the eternal black hole in the thermophile double state grows with time as more Hawking quanta are captured in the radiation region, shown in red on the left panel. And after the inclusion of an island, the entanglement ceases to grow because now both entanglement modes are included in this island union with the radiation bath. So the island formalism for the entanglement entropy essentially has arisen from the quantum extremal surface work of Engelhardt and Wall in 2014, and they proposed this, that the the entanglement entropy, essentially the quantum corrected entanglement entropy, has to be the Ryu Takayanagi plus the effective entanglement entropy of matter fields across this quantum extremal surface, where chi c is the bulk region containing the matter quantum fields. And finally, the island formula for the fine-grained entropy was given in this paper. All this is very well known. So this area term, and then the effective entanglement entropy of A union island of A, where island of A is now here. And we have shown only one side of the eternal black hole. And so this brings us to double holography, and there are three different perspectives that one can look at. So there is this one-dimensional perspective in which we have a quantum, a conformal field theory. There's the bath, and so this is a single subsystem, and there is a quantum mechanical, one-dimensional quantum mechanical system which is there. It could be a possible SYK model or some such thing. Okay. In the two-dimensional perspective, you have a JT brane. Okay, and this is a single subsystem, and this is the island of corresponding to the single subsystem. This is the brane perspective. And if you go to the bulk perspective, this is what is double holography. So you consider that this CFT is holographic and is described by some ADS tree, and there is a Planck brane, and this RT surface actually computes where the RT surface lands on the brane, okay, and it computes the island corrected entanglement entropy already. Okay, very good. All this is fairly standard. So I don't think this has been reviewed in this. So this brings us to what I was saying earlier, that it is possible to look at a more nuanced structure of entanglement by looking at mixed states in subsystems, mixed state configurations in the radiation bath, okay? And it gives rise to very interesting phase structures. So this was this was done for reflected entropy in these two papers. They came on the same day, I think. And so for a bipartite state, mixed state in a quantum field theory coupled to semi-classical gravity, the reflected entropy, the fine-grained reflected entropy will now be given by this kind of a formula, where this is boundary, the intersection between the boundary of the reflected entropy island and the reflected entropy island of A and B, okay? And the S effective for the quantum matter fields will now be given by A union reflected entropy, reflected island of A, and B union reflected entropy, reflected island of B. So you see there are two different islands now. There is an island of A union B, okay, which is the entanglement entropy island, and the reflected entropy islands actually splits the entanglement entropy island according to this. So basically the candidate reflected entropy island, ISRA and ISRB, are chosen by splitting the entanglement island as ISRA union ISRB, and this should be given by the entanglement entropy island IS A union B. So in general, this is to be noted that ISRA is not equal to IS of A. may intuitively be understood as the island prescription applied to the reflected entropy, which is the von Neumann entropy of rho A star in this purified state rho AB. And if we apply double holography, we can see that now the EWCS can end on the brane precisely at the location of this point Q, which splits the entanglement entropy islands into two in the lower dimensional effective theory. There's a mistake actually, this is not an end of the world brane. Okay. The ADS BCFT correspondence due to Takayanagi. Yes, you have a question? Yeah.
Is it necessary for the two islands to be adjacent to each other?
This one?
Yes.
Yeah, it's necessary. That's what we gathered from these two papers. Yeah.
So why these two islands must be adjacent to each other?
Sorry, beg your pardon?
Why are these two islands must be adjacent to each other? I mean, in the figure.
Okay, I understand your question. Yeah, there could be situations in which these.
Yeah, like there is some.
You're saying that there's a gap between these two.
Yeah.
Okay. I don't think such a situation occurs. Okay.
Is there any reason
I cannot remember any argument against that right now, but I don't think that the examples we have looked at is really.
So you mean those are not favored in this extreme?
I think so, but I'm not sure. Okay, so maybe we can talk about it. Okay. So this ADS BCFT correspondence due to Takayanagi given in 2011. There's this boundary CFTs, a theory is defined on manifolds. It's a very well known example of CFT2 restricted to a half plane. Okay, and typically we have a boundary which respects conformal boundary conditions. And the gravity dual of such BCFT2s are described by ADS tree geometries. And the image, the holographic image of the boundary is a end of the world brane, just like a Kirch-Randall brane. And the RT prescription is modified in this case to allow the RT surface to terminate on the end of the world brane. So you have a connected phase, whereas here you have a disconnected phase where the RT surface actually lands on the brane. Yes, sir. Yes, there's a Kirch-Randall. Even before Tadashi is probably, yes. Okay, thank you for pointing it out. Yeah. Okay, so now we come to this model of Gang, Randall, and Swanson. So there's a holographic BCFT2 on a black hole background. So you begin with an eternal ADS3 black string geometry truncated by an end of the world brane. And this is the metric. And so the geometry on each constant row slice is an eternal ADS2 black hole. And the dual boundary conformal field theory is one such eternal ADS2 slice at the asymptotic boundary, rho equal to infinity, with conformal boundary conditions at u equal to 0. So the coordinates over here, we are looking at a time slice, okay? A fixed time slice, and this u is a radial coordinate, UH is a horizon, okay? And this slice is rho equal to, and the rho is an angular hyperbolic angle, okay? So rho goes from 0 up to the rho b, this is the brane, so this is the brane angle, and up to rho equal to minus infinity, so, and u equal to 0, okay? Very good. So now we consider a subsystem, a disjoint, a subsystem which is given as 0L, UL, union 0R, UR. Sorry, I should have also mentioned that the other side is the thermofield double, okay? Because this is an eternal black hole. So consider a subsystem, A union A, given by this union of these two disjoint subsystems on the asymptotic boundary of the bulk geometry. And the entanglement entropy between A and its complement is, sorry, this is a typo, is given by this, okay? And since the BCFT is located on a curved background, so to compute the E is required to transform this to a conformally flat geometry. And to achieve this, we first map the eternal ADS2 black hole to a semi-infinite thermal cylinder described by the coordinates u star tau under these transformations. And then there's another map given by this, where one can take this cylindrical geometry to the plane with the disk WW bar less than equal to UH square removed. And the metric in this new coordinates is given as this, where this is the conformal factor. And it is possible to further conformally map this geometry to the upper half plane through these transformations, and the conformal boundary is now mapped to the real axis, V minus V bar equal to 0, and the metric changes to this. So this is a pictorial representation of what we are looking at, okay? So this was a cylinder, and then from this to the plane with this thing cut out, and this finally mapped to the upper half plane. Now, utilizing the boundary and bulk channel expansion of the twist field correlator, and the appropriate conformal factor, it is straightforward to compute the E of the subsystem A in the boundary channel and the bulk channel. And you can see in the boundary channel, there is this contribution of the boundary entropy 2 log GB. And in the bulk channel, you have this. And log GB is the usual boundary entropy in ADS3 BCFT. Very good. So if we look at the phases of the entanglement wedge cross-section for these two disjoint subsystems, we will see that if you consider the generic configuration of two disjoint subsystems A and B, there are 4 different entanglement entropy phases for A union B based on sizes and locations of the subsystems, and these are investigated. Within each E phase, there are different entanglement wedge cross-section phases as depicted by the dashed lines. So it depends on the location of the subsystems and their sizes where the entanglement wedge cross-section will land. So you see in this phase 1, A union B are large and far away from the boundary, so you have different phases of the entanglement wedge cross-section. Okay, and this final one is the disconnected phase. Okay, so if you want to consider the reflected entropy, now we consider the generic configuration of two disjoint subsystems again, given by these coordinates in U for the TFD double. And there are 4 different AE phases depending on the sizes and location of the subsystems. Within each E phase, different reflected entropy phases are observed. And the corresponding Renai reflected entropy now may be obtained through the following twist field correlator. So this is 8-point twist field correlator in the BCFT. And the above twist field correlator may be computed in different limits of the subsystem sizes and locations where suitable large C factorizations are observed. Okay, so for example 1, that is basically this one. Okay, we have both subsystems are large and far away from the boundary, and for this case the relevant OP channels are these. Okay, so you have this 2-point function. Okay, and they are far away from the boundary, so there are 2-point functions between L1 and R1, L4 and R4, and there is a 4-point function between L3, L2, R3 and R2. Okay, and the 8-point twist field correlator factorizes into 2 2-point twist field correlators and 1 4-point twist field correlator. And since this is all the subsystems are large and far away from the boundary, so we directly these correlators go over to the CFT and we don't have any boundary effects over here. Okay, so the reflected entropy now is given by just this, because the 2-point correlators, they cancel from the numerator and the denominator, and you have to take care of the conformal factor because this is on a curved background, a fixed curved background, there's no dynamics there. And once you do the transformation and go through the computation, this is the reflected entropy in the large central charge limit, and where the cross ratios are these complicated results which are not very interesting. Okay, now if you look at example 2 and we consider subsystem A is close to the boundary and large while B is far away, so namely that is basically this one. Okay, now you see there is a possibility that the entanglement wedge cross section can land on the end of the world brane. Okay, so now the twist field correlator now factorizes, and you have to take into account boundary effects. So you see there are basically the 8-point twist field correlator factorizes into 2 1-point and 3 2-point twist field correlators. So 2 1-point, okay, and 3 2-point twist field correlators like this in the boundary conformal field theory. Now when you use the doubling trick to map these twist field correlators to the chiral twist field correlators in a conformal field theory defined on the full complex plane, the Renai reflected entropy for this phase is given as this. So there are, so the 2-point twist field correlators, once again they cancel away, and this is just the basic CFT correlator as it is away from the boundary, and here you have these 4 points. Okay, so these 3 cancel out, namely this, this, and this. And you have now only 2 4-point correlators in the CFT. And if these are evaluated in the standard large C limit, the reflected entropy is given by the sum of these 2 terms. The first term comes from here, and the second term comes from here. And eta I once again are the cross ratios, And the boundary entropy, S boundary, arises from the OP coefficient, CNM, in the 4-point twist field correlator. And this is given by this following. So if you now look at the corresponding bulk calculation, now I should remind you that we are actually, remember, I had shown you this 3 different perspectives. We are actually working in these 2, okay? We are not really looking at the 2-dimensional perspective, so we won't have explicit islands, but it is well known that when we do the double holography, the island contributions are automatically incorporated. Sorry?
Part of the brain is the island.
In which one? Okay. Right.
This is an island. The part which is.
You are saying this, right?
Yeah, exactly.
Yes, there is an island. Yeah, but actually you only compute the RT surface in the bulk, right?
Correct. But that's the same as the island.
Right.
This island in this.
Right. Absolutely. Yeah. I mean, what I meant was that they're not explicit in this particular bulk calculation. Okay. So, yeah. So if you look at the entanglement wedge cross section. So in the embedding space formalism for ADS-TEE geometries, this is explained very well in Kuzuki and Tamaoka, okay? And this is the formula which they worked out for the, and this, in this formula, U and V are given in terms of the scalar product of the, of xi dot xj, okay? And U and V are given as this. And the EWCS for 2 adjacent subsystems is given as this. If we will need these adjacent subsystems when we are looking at 3-point functions. And the dual bulk geometry described by the ADS-TEE black string may be embedded as a codimension 1 surface in R2, 2 through a given parameterization. But this was actually, this formula was very helpful in computation. Okay, so now if you look at example 1, again, so you consider both the subsystems are large and far away from the boundary. The bulk entanglement wedge cross section for this case is given as the length of the green curve shown in the following figure. So you can see that this is actually a Hartmann-Maldacena surface as it crosses the horizon. Okay. And the bulk EWCS can be obtained by utilizing the embedding coordinates for the points L2, L3, and R2, R3. Okay, so you can see that this is landing from this RT surface to this RT surface, and with U and V given as this. So if you just substitute all these things, the reflected entropy computed earlier in the example 1 by a replica technique exactly matches with twice the bulk EWCS if you utilize the Brown-Hanno relation. So that's very comforting. Whereas for, in example 2, consider the subsystem A is close to the boundary and large, while B is far away. Okay, the diagram is not to scale, so it doesn't really, the diagram really doesn't show that this is, but just stay with me that A is close to the boundary and large, where B is far away. Okay, and now we compute this, the RT surface can now, sorry, the entanglement wedge cross section can land on the brane. The length of the geodesic may be computed upon utilizing the embedding coordinates for the L2 and L3, and the brane is at a fixed brane angle. Okay, so this is rho B. So these coordinates, they are not written down over here. So this UB and rho B, and there is it's on a fixed time slice. So the length of the geodesic can be the arbitrary point on the brane. Okay, and this point UB is not fixed. So you extremize this length over UB, and then the bulk EWCS may be obtained like this. Here also, when we use the Brown-Hanno relation, the preceding expression of the bulk EWCS equals half of the reflected entropy calculated in example 2. Once again, verifying the holographic duality between the reflected entropy and the bulk entanglement wedge cross section. Okay, so we come to the page curves. So for the case 1, page-like curves, I should say, for the reflected entropy, for sufficiently large brane angle. Okay, so case 1, the subsystem A is close to the boundary. This is for the entanglement entropy. So you see this cyan curve, not cyan, so this magenta curve. Okay, so this is the minimal of there are 3 entanglement entropy phases. Okay, phase 1 and phase 2. For sufficiently large brane angle, we observe the EE transition between phase 1 and phase 2 at page time, T disjoint 1 to 2, and between phase 2 and phase 3 at page time. So this is in the EE phase 1. Now, if for each entanglement entropy phase, the reflected entropy will have, so in the EE phase 1, you see there are 4 reflected entropy phases, okay, and this cyan curve is the minimum of all this. So after transition, the reflected entropy initially rises with a very slight slope and then slowly falls until T disjoint 1 to 2, as the growth rate of the bulk EWCS, which lands on the Hartmann-Mallichner surface, is lower than the EWCS described by the Hartmann-Mallichner surface itself. After this time, in the EE phase 2, the reflected entropy increases again, okay, it increases again. Initially, the reflected entropy increases again and transitions to a constant value, okay, it increases again and transitions to a constant value until you reach this, the third phase, T disjoint 2 to 3, as the bulk EWCS lands on the RT surface, which does not cross the horizon and is thus time independent, okay. So you get this, which is a constant. So finally in EE phase 3, the reflected entropy saturates to a smaller value. And furthermore, from the inset graph, we compute the deviation of the Markov gap from its saturation value, okay, and we observe a non-negative value for all times. So that means the Markov gap is always positive. That means the reflected entropy is from its saturation value, and we observe a non-negative value for all times, which is consistent with its geometric interpretation and shows a rich behavior. Now, these kinks and essentially what we think is that it is because we have not, if you consider all possible saddles, here only the, I think just the Hawking and the replica wormhole saddles are considered, and we think that this is the reason. We are not sure that if you consider all the saddles, then these kinks should smoothen out. But that's a conjecture. I'm not sure that, I mean, I don't have a proof for it. And for case 2, when the subsystem B is far away from the boundary, the E phase transition between phase 2 and phase 4 occurs for a small brane angle. Sorry, I should have mentioned that this is for a large brane angle, subsystem A close to the boundary and a large brane angle, okay, and this is for a small brane angle. The E phase transition between phase 2 and phase 4 occurs for a small brane angle. From the page curve of the reflected entropy, we can observe that in the E phase 2, the reflected entropy increases initially as the bulk EWCS is the Hartmann-Mallichner surface, which grows over time and then remains constant until the page time as the bulk EWCS lands on the end of the world brane. So essentially it is this and this, okay. So after the page time, the reflected entropy, this is a typical eternal black hole page-like curve. Reflected entropy saturates to another smaller constant value in the E phase 4. So this is the phase 4. So there's a transition from phase 2 to phase 4, okay. And if we now go to the reflected entropy diagram, okay, so this is for the entanglement entropy. If you go to the reflected entropy diagram, we see that after the page time, the reflected entropy saturates to the smaller constant value in the E phase 4, okay. So once again, you see this cyan curve, okay. It just goes from here. This is the minimum of all this. So there are 1, 2, 3 phases over here, and these are 2 phases. So basically it saturates to a smaller value over here after the page time. Saturates to a smaller constant value in the E phase 4. So furthermore, if you look at the inset graph, it shows that the deviation of the Markov gap from its saturation value is once again always non-negative, which is consistent with its geometric interpretation. Okay, so I'm at the end. I think I've kept very good time. It's only 6 minutes left. Okay, so summary, we have described an example of mixed state entanglement of disjoint subsystems through the reflected entropy in a Kirsch-Randall brane world model with a radiation bath involving a boundary conformal field theory in a ADS2, fixed ADS2 black hole background. The reflected entropy was computed through a replica technique for the disjoint subsystems in the bath BCFT2, and it was matched with twice the bulk EWCS, verifying the holographic duality between them. We demonstrated the emergence of a rich phase structure for the reflected entropy for each entanglement entropy phase. The corresponding page-like curves for the reflected entropy was obtained for different values of the parameters describing the subsystems and exhibited the corresponding transitions between the different phases. We also compared the reflected entropy with the mutual information to investigate the Markov gap through its deviation from the saturation value. So there's future directions. It would be interesting to study other mixed state measures for such brane world models and study their phase structures and corresponding page-like curves. And this is a much more challenging issue. The second one, the possible generalization to multipartite entanglement, is a very challenging issue. So the bottom line is that despite interesting and exciting insights, the saga of the information loss paradox is far from over, and further progress remains to be charted out in the future, leading to new and more clarifying perspectives on this perplexing puzzle. finally, thank you. And this is a photo I took in the first morning that I saw from my balcony, okay? And this was really very beautiful. And I propose that if you take an analytic continuation of this photo, you will reach some Monet painting, okay? So this is a Monet's cube, okay? So I'm coining this word now. Thank you again for this beautiful conference and for the warm and generous hospitality.
You saw this non-monotonic type behavior in the Markov gap, right? It goes up, down, and so on.
Yeah.
Is there any intuitive interpretation you have for that?
That's what I was saying. I mean, are you referring to the kinks, etc.?
No, not the kinks, just the fact that it like goes down, goes up again.
It should, according to the paper by Onkar, Hayden, and Source, that it should always remain positive, right?
Yeah, I just meant as a function of like in your plot.
Okay.
Like it should be positive, of course.
Yeah, you're saying this kind of a thing?
Yeah, that sort of thing, yeah.
Okay. No, I don't have an explanation for this.
Okay.
Maybe Onkar is some, yeah.
Yeah, why doesn't it just have a monotonic sort of
I see,
thing?
okay.
Yeah. Okay.
No, I don't have an answer for this. I have not thought about it, but it's an interesting question. Maybe I